I hope you're able to see my screen. Today we will leave cyclopentadiene chemistry and move to arene chemistry. And by now you're probably familiar with the fact that pi complexes of metals are practically possible with any pi system, and arene complexes are just like cyclopentadienyl complexes. The surprising thing is benzene is an extraordinarily stable compound. So you would want to know why it forms a complex in the first place. So why should an aromatic compound which has got extra stability form a metal complex at all? So this is basically the principle of give and take. If you want to have the stability of the whole system, I have to consider the stability of the benzene and the stability of the metal, and the metal is left without any other electron density around it, and it is severely electron deficient. So it will have to interact with the metal in order to form a stable system. If you give an isolated metal atom and an aromatic ring system, then this has to form a complex in order to be more stable as a whole. So that's really behind the formation of arene complexes. You need to generate metal in zero oxidation state, and you need to have systems where there are no other coordinating ligands, because something which is better than the arene is going to be displacing the other the arene ligand from the coordination sphere. So let us just go back to the ligand map that we talked about early on. As I mentioned, the odd carbon species are listed above this line. So below this are all even carbons. Here we have all the odd carbons. So we have progressed slowly all the way up to cyclopentadienyl. Of course, we can go to C7. That's also an odd species. But like I said, having a ligand system which is larger than 5 or 6 is tough on the metal, because it has to be coordinated to all 7 atoms at the same time, and the distance becomes fairly large. So C5 is the ideal. Just like C5 ring systems in organic chemistry, C5 and C6 are the optimum. Beyond that, it becomes unfavorable. Now, if you look at the 6-membered rings, obviously 6 would be an upper limit, but we do have C8 ligands coordinated to metal ions or metals, especially uranosine, lanthanides and actinides. Lanthanides and actinides do form complexes with C8, but in general we would stop around C6 as far as 3D, 4D and 5D transition metals are concerned. The most stable systems are like that. So we have pretty much covered the whole periodic, the whole ligand space. That's like the periodic table of metals that we have on the other side of the system. So let's talk about the discovery of bis-benzene chromium. It turned out to be an accidental discovery. It was made by some people and left uh, as insoluble difficulty because the bonding, as this was 1950s, this was not very clear what the bonding was, and to top it all, it was the monocationic species that was made by one of the students of Fischer, and it was Hafner who successfully found a system which would reduce this reaction mixture to generate the bis-benzene. Yeah, so thus, yeah, so uh, so let me just tell you that there is a very nice article on this whole bis-benzene chromium discovery, and this was published in 2002. And I'm going to briefly show you this paper. This is in Organometallics 2002, 2800, page 2800, 2002 and 2800. Easy to remember, but of course this will be in the video now, so you can go ahead and take a look at this paper. I would strongly recommend it because it's very easy to read. Although it's 20 pages, if you read the first few pages, you will get the gist of the discovery of bis-benzene chromium, and it will give you some hints about how exactly people have to do chemistry. Okay, so this was yeah. Hafner finally, of course, developed a more rational method of synthesis. What he did was he used aluminum powder as a reducing agent. Aluminum powder as a reducing agent. In these cases, it's not very clear why you always end up with chromium 1 complex. Of course, you are starting with CrCl3, but you are reducing it with a very strong reducing agent, which is aluminum. Very strong reducing agent. This is a strong reductant. So, in all probability, in those days when Fischer originally started his work, they started with a reaction system which was not so amenable to air sensitive compounds, to the discovery of air sensitive compounds. Right now, in most German labs, they use a heated column to reduce the traces of oxygen that come in the nitrogen gas that they buy. So it's mixed with 1% of hydrogen and then pass through a heated column, heated copper column. So this heated copper reacts with oxygen very rapidly. This is known as a BASF R311 catalyst. BASF R311 catalyst. And this catalyst is capable of reducing oxygen at room temperature, but then at higher temperature, with this 1% of hydrogen, the copper oxide is reduced back to copper metal. So this is a dynamic system that they use in order to have extra pure dinitrogen. They don't give any chances for oxygen to be present. So this reduction with Na2H2O4 is also a strange reaction because it requires sodium hydroxide to convert SO3 2 minus to SO4 2 minus and liberate 2 electrons. So you used a very strong reducing agent and a mild reducing agent after the compound is formed to generate the chromium complex. Fischer-Hafner synthesis, according to the book, will work with many metals, but it doesn't work here. It doesn't work with manganese. Manganese, I can understand. Manganese is something that has got a D5 configuration in its +2 oxidation state, and so it has a tendency, it's D5S1 in its neutral state. So, oops, sorry, that's a D5 is the D5 is the electron count. So what happens is you have disruption of the symmetrical nature by Anteller effects. So this is probably one reason why the manganese complex is not stable. But why niobium and tantalum also do not form through the Fischer-Hafner synthesis is not very clear to me. I will leave that as a thing to dream about, but let's move on. ARX also, there are some limitations. You can't use any arene ring. All arenes do not work. All arenes do not work. Benzene, naphthalene are all fine. If you have any halogen on the benzene ring, it doesn't work. Any halogen will not work. Any NH2 group or ether, this will also not work. According to Elschenbroich, this is because of AlCl3. AlCl3's function is stopped when you have coordinating groups on the benzene ring. So it seems to me that it is not just AlCl3, even chromium will prefer the pair of electrons which are present here to the benzene ring, and the reaction doesn't proceed as you expect it to proceed. There is one unusual reaction, and that is the trimerization of dimethyl acetylene. This is unique to dimethyl acetylene. It trimerizes to give you hexamethyl benzene complexes of chromium. And here also there is something strange. You're adding both water and dioxygen, and then you have to reduce it. So it's not so clear to me why they do these things, but this is Fischer's group. And Elschenbroich is an authority on benzene complexes. He's a person who's written the book on organometallics, one of the best books that are there. So let me now come to a standard method of making any arene complex you want. And that is because you evaporate the metal to a gaseous state. In the previous instances, the M in plus N oxidation state was reduced with a reducing agent like aluminum. Here, you take the metal in the zero oxidation state and vaporize it to monometallic species, right? So you have a gaseous metal atom, but this metal atom is not going to be stable. You can deposit it in a glass vessel, on the surface of a glass vessel. Let's cover this with liquid nitrogen. So this is at minus 196. So the glass vessel is coated. We can use a different color. Let's say the glass vessel is now coated with the ligand. Is coated with the ligand, and the metal is evaporated from a crucible. So the metal is evaporated from a crucible and it goes and deposits on this on the surface of this glass vessel. What that does is it provides metal atoms which are surrounded by the ligand atoms. The metal has no choice but to coordinate to the benzene ring because there is no other coordinating group available for it, and the best group is the aromatic ring system, so it forms aromatic complexes fairly easily. Okay, what you have to do though is to warm up the reaction this reaction system after the reaction, because this vaporization and co-condensation is usually done at liquid nitrogen. The reaction itself is very wasteful. It requires 40 to 60 liters of liquid nitrogen for making 500 milligrams of the metal complex. So if you want to evaporate the metal, you have to use a very high temperature. And at that temperature, the ligand will not survive. So you have to cool the ligand to a very low temperature. And this heating and cooling is very wasteful. And that's why it's not a very popular method, but sometimes one has to resort to that. Especially when you have groups which are reactive, like chlorine. This is the only method by which you can make it. So this is the reason why Elschenbroich is saying that AlCl3's function is stopped, because here you do not have AlCl3, you have the metal atoms. So the metal atom has a choice. It can coordinate to the lone pairs on chlorine, it can coordinate to the double bonds, but then the double bonds are like a chelated system and seem to win over in this battle for the metal atom. And so benzene rings form complexes. The stability of, these systems are around 170 kilojoules per mole, whereas cyclopentadienyl complexes, ferrocene for example, is around 296 kilojoules per mole. So there is a big difference in the stability of the benzene complex with respect to the ferrocene. The ferrocene is more stable because you have a charge species Fe2 plus interacting with the Cp minus. So that is also increasing the stability of this system. Okay. So Elschenbroich in fact made Elschenbroich, and there's another person in the US, I forget his name just now, but Lagowski, yeah, Lagowski and Elschenbroich made several interesting metal complexes, especially when you have alkyl groups on the benzene ring. AlCl3 cannot be used because AlCl3 has a tendency to scramble the alkyl groups on a benzene ring, because the Friedel-Crafts reaction, strange as it may sound, is actually reversible. You can, if you use AlCl3 on a heavily alkylated system like the tris tertiary butyl benzene, you can have scrambling of the position of the alkyl groups. So this is the best way to make it, the co-condensation route. Okay, co-condensation route was the best way to make benzene complexes. He also made some exotic complexes. One of you asked whether you can connect two ring systems. Yes, here is one case where the connected ring system is used and then the metal atom is introduced through co-condensation. So these are some of the systems that were made. Let me now go to the fourth method of making this complex, and that is a ligand exchange. although these complexes are bound through 3 different points of attachment, what I'm talking about is the 3 different points of attachment that I'm referring to are here. It looks as if, or it's the equivalent of 3 double bonds interacting with the chromium. So can you really remove it? This is why I mentioned it as a chelated ring structure. Chelated ring structure. But now, if I have a ring system, can I exchange it with another ring system? The answer is yes, but not when it is benzene. What I'm saying is benzene itself seems to be non-exchangeable. Okay, it's one of the best ligands. It's just like ethylene. Okay, ethylene turns out to be one of the best ligands for any metal system compared to other substituted ethylenes. Similarly, benzene, chromium seems to be a very stable system. But if I have naphthalene, then the naphthalene can be exchanged with another ring system to form a species like this. Okay, so this kind of exchange seems to be feasible, and that is probably because you can form, if you count the number of electrons, you will find that this is an 18 electron species. But if I move it slightly, I can make a 16 electron species, bring in another ligand system, and remove the old ligand system. So temporarily I can form 3 benzene rings coordinated to 1 chromium and then replace the next aromatic ring system. The last method is the reductive complexation method that is mentioned in the book. The reductive complexation method, you use a lithium organometallic, where the lithium is actually has transferred the electrons to the other ring system. This is C10H8. Now this can hold 1 electron, so it forms naphthalene minus dot, right? So it's a radical anion. This radical anions are capable of reducing the metal to M0. So if it does that, then the M0 can coordinate with the C10H8 to form a complex. In order to stabilize this electron, you need more than 1 aromatic ring system. So that's why I said naphthalene is a minimum size for the ring system. Minimum size. You can have larger ring systems like anthracene. Anthracene would also hold an electron as a radical anion, and you can reduce many metal ions, MX2, MX3, MX4, like that, and reduce them. At the end of the reaction, because you might have used excess of the reduced species, the reduced species are oxidized with iodine in order to get the final compound. So these are very specific to the metals that you're discussing. So the principle is this, that you use the aromatic ring system as a reducing agent, okay, and as a ligand, as a reducing agent plus a ligand. So that's the trick that they have used in this. Okay, now we have not talked about the electron count or the electronic structure. The electron count in bis benzene chromium is 18. Bis benzene chromium is 18 electrons. The moment you go from chromium to manganese to ruthenium, you have 2 extra electrons on the ruthenium. So the best way for a bis-arene compound of ruthenium to form a stable complex is to do a eta 4 binding on one side and a eta 4 binding on one side and a eta 6 binding on the other side. This would make it a very stable system. The advantage is this, because you have 3 isolated double bonds, you can flip the position of the metal from one place to the other place. Excuse me. So I can have an alternate position. So the metal can, in fact, this is difficult to draw, but let me try. So the metal can move from one position to the other. I'm imagining the ring system to be above and the metal to be below in a plane. Okay, and the metal keeps moving around. I will show there are complexes which are there, which are more exotic, which we will discuss shortly. But basically what I'm trying to say is that the 18 electron system is fairly sacrosanct. You don't increase the electron count by any means. You can decrease because you have non-bonding orbitals in which you're pumping in the last 6 electrons, as we discussed in cyclopentadienyl complexes. Here also you will have 6 electrons in 3 orbitals which are mostly non-bonding. That results in complexes with less than 16 electrons are okay, but not more than 16 electrons. So X-ray reveals complete bond localization, but NMR suggests that the metal is moving about and it looks as if it is a 20 electron complex. Okay, let me see what I have done. Yeah, let me complete this discussion. So you can remove those 2 electrons. You can form a dication. This seems to be possible. And then it is a eta 6 system. As a dication, it is susceptible to reduction in terms of a reducing agent like borohydride. Then it forms a cyclohexadiene complex of eta 4, eta 6 complex of ruthenium. So that's also possible. So let me see what I have here. Before I go to the electronic structure, let me say what happens when you have rhenium. Rhenium seems to be an interesting case. With hexamethyl benzene, it forms this 19 electron species. Okay, but then this has got this 1 electron extra, which can in fact function like this. So we have rhenium is in the manganese group. So you have 1 extra electron, and so it forms a species like this. But then this radical is capable of dimerizing with another rhenium species, and it forms a dimer. So this is 5 electrons from here, 6 electrons from here, 11 plus 7 from rhenium. So it forms a 18 electron system which dimerizes. So that's the stable form of rhenium. It looks as if it's a 19 electron complex, but it looks as if it is C12 R12 rhenium, but it is actually C12 R12 rhenium twice. Okay, so it still forms a carbon-carbon bond at this position, so that it dimerizes to give you this species. Sorry, I forgot to put that in as a slide. So let's briefly talk about the electronic structure. See, this benzene chromium forms a completely eclipsed structure. By the way, I noted that in the metallocene lecture, I had interchanged eclipsed and staggered forms. I was extremely embarrassed when I listened to it, because this was probably like talking in my sleep. I should have realized that the eclipsed and staggered forms are what they are. This is eclipsed D6H, and in the lecture I have, in one place in the beginning, I have interchanged, and none of you stopped me. So either you are also sleeping and you're not listening. So eclipsed form is when the two rings are completely overlapping with one another. So let me just see if I have that. So this benzene chromium. So let me see if I have this benzene chromium. One second. I will draw that for you. Yeah. So this is the eclipsed form of bis-benzene chromium, and that is the only form that is known. Surprisingly, it's not like the bis-cyclopentadienyl iron complex, where the staggered form is known. Here, the bis-benzene chromium forms only the eclipsed form. So I think it was Pankaj or somebody mentioned that the eclipsed form must be the more thermodynamically stable form, even for the iron system, and that's roughly seems to be the case in this case, at least for sure. I will show you something more about the bis-cyclopentadienyl system, if time permits, at the end of this lecture. Okay, so let's move this out. So here is the bis-benzene chromium. I'm not going to go through it in detail, but the principles are exactly the same. You take the 6 molecular orbitals of the pi system of benzene, and they will form the most symmetrical combination at the bottom, and 2 degenerate orbitals which will also be filled. So that will account for 6 filled orbitals on 6 filled orbitals on the benzene ring. And if I have 2 ring systems, then of course all of them will be filled. 2 benzene rings are there. Now plus and minus combinations of these 2 ring systems, so you will have one face-to-face and one head-to-tail arrangement, head-to-head arrangement and head-to-tail arrangement of the 2 benzene rings in a parallel fashion will give you total of 12 MOs. Right? These 12 MOs will have some combinations which do not have suitable metal orbitals. With this symmetry. So I need to indicate that it is not available. Okay. So these 2 are non-interacting. These are completely. They are also virtual. That means they are not filled. These are also not filled. empty. These are empty and interacting. These are empty and cannot interact because there are no metal orbitals which have that symmetry. So you take the metal in D6H symmetry and look for the various orbitals which are available on your right hand side and interact them with the suitable combinations on suitable combinations of ligand orbitals on the left hand side, and then you form these molecular orbitals. You do not even need a computation, but you can draw out the various combinations, and that's what I suggest that you do. You should be able to match these orbitals, especially when the symmetry is good. It's not too difficult at all. So this combination will interact with dz squared, for example. This combination will interact with the pz. So we are okay. I have to I have to tell you that this you forget this what is written here. If I use the dz squared and pz, I am assuming that this is the z-axis. Okay. So so you need to be careful about definition of the axis before you decide on the way in which these orbitals interact. So the simplest way to do it is to assume that this is the z-axis. Then you can have the type of interactions that are easy to visualize because of the way we combine two degenerate orbitals to derive the dz squared. Okay, so dz squared has got a special shape, and that special shape assumes that it is the unique axis. Okay, so let me leave this discussion and talk about. Okay, let me see where I'm headed. Yeah, so let me go back a little bit. Yes. Yeah, so I needed an empty slide, but I have not done that. So let me just draw it out in this slide. So if you look at the chemistry of metallocenes, I emphasize that there are two specific. One is the similarity to benzene type reactivity. Okay, and the other is the redox reactions that we talked about. When it comes to bis-benzene chromium, so you already have an aromatic system. So this aromatic system has been modified by the metal. So what you end up with is some kind of enhancement of some reactivities as far as aromatic ring systems go. So for example, if I want to do Friedel-Crafts alkylation with this, I can do that, but then I will end up oxidizing the metal. Chromium will become chromium plus. So there are not many reactions that one can do with bis-benzene chromium. It's more or less like an ornamental system compared to metallocenes like ferrocene. Ferrocene is more rugged. This decomposes around 300 degrees centigrade, but it decomposes. It doesn't sublime the same way in which ferrocene does. Ferrocene is very easy to volatilize and so on. So bis-benzene chromium also sublimes, but it is not as stable as ferrocene. So if you want to do some reactivity also, it doesn't have the same reactivity pattern that the metallocenes based on cyclopentadienes are concerned. Here the reactivity is much less, but you do have reactivity which is similar to aromatic ring systems, just like the benzene ring. And this is alkylation can be done. You can also do lithiation, and lithiation also happens in both rings. The way in which I mentioned to you, both rings get lithiated. So that type of reactivity is known. But you do not have isolation of the double bonds. That is, bond localization is not observed. Okay, bond localization is not observed. So most of the chemistry that is done with aromatic rings coordinated to metal atoms come from half sandwich complexes, which we have not talked about so far. These are half sandwich complexes. Half sandwich complexes have got on one face, these are like Janus faces. If you know what is a Janus face, one side it looks like a metal carbonyl, on the other side it looks like an aromatic ring coordinated to molybdenum. So there it has got two faces. So these are complexes which can be made, half sandwich complexes, and then the reactivity is much better. Reactivity and stability is better. This seems contradictory, but stability with respect to oxygen and water, reactivity with respect to nucleophiles and electrophiles. Okay, so let's talk about half sandwich complexes. The way to make half sandwich complexes is through a reaction of a metal carbonyl directly with the aromatic ring system. This is a very convenient, easy way to make it. Instead of displacing it with, when we discuss carbonyls, we said that 3 ligands can be displaced. 3 are displaceable. Why? Because 3 carbon monoxides are competing with the other 3 carbon monoxides in the trans position for pi bonding. So if you replace it with the poorer pi acceptor, then the metal is happier, the carbon monoxide is happier. So aromatic ring systems are poorer pi acceptors compared to carbon monoxide. Something which I did not discuss in the ring system. Elschenbroich mentions that the gap between the sigma and the pi in this is slightly higher than in the case of metallocenes. Okay, so the bonding orbitals give more electron density. So the destabilization of the dxz and dyz is greater than in the case of metallocenes. Okay, so this turns out to be the reason for the higher gap here. So that means they are better donors. Okay, yes, they are better donors, and they destabilize the dxz and the dyz orbitals, making this gap larger. So if you look at these ring systems, you have on one side you have a benzene ring, the other side you have a tricarbonyl, and as I said, they are more stable than the bis-benzene complexes. These are variations that I have put up on the slide. You can see that manganese has lost 1 electron, so this is equivalent to the chromium complex that we had in the previous slide. So let's now talk about some other reaction here. I have two complexes being formed. This is a reaction which we will have to discuss a little more later on, but this is a case where you can have an aromatic ring with two groups, and you can have them in a chiral form purely because this is a pseudo 4 coordinated system. Okay, so you have three groups which are a virtual group here. So three groups on the top and one on the bottom. That is the three carbonyls. So that's why you have two different. And if you have R as a chiral, these will be diastereomeric products. So I should not have put it here, but it's okay. You notice that that possibility is here in this case. Okay. So let me now talk about some cases where the bond is frozen in the benzene ring. I told you that bond alternation is usually not observed, but if the metal atom like ruthenium has to form a 20 electron species, then it fixes the bond positions so that it's eta 4 and eta 6. In this case, it's platinum 2, so it's platinum 2 likes to form a D8 complex. Here it is a D10 system. This is D10. Okay, platinum. So this likes to form a 16 electron complex as well. This likes to form a 16 electron complex, and it has localized the three double bonds in such a way that this is 1.48 angstroms, and this is clearly a double bond. This is clearly a double bond, and this is also clearly a double bond. So the distance of this should have been 1.33, but it's elongated. Actually, I think there is a mistake in the figure. This is 1.51 angstroms, and this is close to 1.48. Okay, so I will confirm this later on, but I think this figure is slightly wrong. So there is elongation of the double bond corresponding to the coordination. So this is more like an alkene complex rather than as a arene complex. So let me now move to another presentation for a few minutes. So we are talking about making them from CrCO6 and just the benzene ring, but you can also form it from a disproportionation reaction. This is bisbenzene chromium and CrCO6, and you can form half sandwiches. This would be this would be something. This is difficult to make, so one would normally not make this complex in this fashion, but for the sake of completeness, I have just put it across. This is possible. But not the best way to do it. You can also directly react it with carbonyls. That's what we have done in the previous case, but now I'm doing it with cyclopentadiene systems. That will also give you half sandwich complexes. So half sandwich complexes can be made with aromatic ring systems like the way we discussed earlier, It can also be done with cyclopentadienyl systems. Here we have a CP Fe CO Fe. This is the ring system that is formed, and this is formed in both cis and trans forms. Both are formed. Cyclopentadiene also reacts with dicobalt octacarbonyl. In this case, it forms the species which we have seen earlier. That's a cobalt complex with 2 acetylenes bonded in this fashion. So this is the half sandwich complex formed from metallocene cyclopentadiene groups. One thing that I did not discuss with benzene rings is the way in which philandrine, this is philandrine, reacts with RuCl3. Here this functions as a reducing agent. It reduces RuCl3 and generates the aromatic ring system, because there are 2 hydrogens here which come out and give 2 electrons. So it can reduce RuCl3 to RuCl2, and that RuCl2 reacts with the ring system to give you the half sandwich complex. If you react this with PPH3, this will now form ruthenium Cl PPH3. Okay, this is a very convenient way of making the monomer. This is the dimer, and this is the monomer that I'm talking about. You can use any L. I used PPH3, but you can use any L in order to generate. This is a general principle. You take any dimer which is halogen bridged, you can add another ligand and generate a monomeric species. And if you have a ligand which is good at making crystals, then this reaction, because this is actually a reversible reaction, this reaction would precipitate out from the reaction medium, forming nice crystals. So that's one way in which you can make this. So since we have talked about half sandwiches, let's talk about half sandwich complexes formed by cyclobutadiene also. Cyclobutadiene also can form half sandwich complexes, and I'm going to take 2 things at the same time. So this is cyclobutene dichloride. 2 reactions at the same time. So this is cyclobutene dichloride reacted with NiCO4. What happens is this compound oxidizes the nickel to NiCl2, and it forms this cyclobutadiene complex of nickel, which is a dimer again, which forms a dimer again. Remember, this is now nickel 2. So there is another chloride here. Yes. Okay. So actually, it would be better to put a cycle, a ring here, because it's a cyclic ring system. There are no isolated double bonds to talk about. This is better. So you can do this with iron also. Iron and nickel are capable of doing this. So the side product here is FeCl2. You can do it with nickel and iron, and here we have a reaction which is an extrusion reaction. If you remember, I told you that some groups can be extruded in order to form a smaller ring system, and here is a good example where you have, now again this is a dimer, this is a dimeric structure, but the dimeric structure has been formed from the tin being extruded from the reaction mixture. One size down, we started with 6, we came to 5, then we came to 4, now we have come to 3. Cyclopropenyl cation. Cyclopropenyl cation is again an aromatic system. So unlike cyclobutadiene, which is anti-aromatic, this is an aromatic ring system. This can also form complexes with a metal. So this is illustrated with a nickel tetracarbonyl forming this nickel dicarbonyl species. This is again a dimeric species which is isolated from this reaction mixture. So one unique feature of this compared to the previous ring systems that we discussed, half sandwich complexes that we discussed, is the fact that this is considered as a negative charge, then it is nickel 2 plus. Okay, I think I have to stop here. I have lost track of the time. Yeah, I think I will stop here. There are some more species that we can discuss that, but I will not discuss them today. I'll probably post it as a small addendum. We can have half sandwich complexes formed through other means. Maybe I will just show you this. Uranosine forms cyclooctatetraene. Okay, I have already told you this, but uranosine forms cyclooctatetraene. So let me stop here and ask if you have any questions. I have to post the 1 second. I have to post the structure of cyclopentadienyl complexes. I think both D5D and D5H structures are possible. They are very slightly separated in energy, but both of them are possible. And I will discuss them later. Pankaj, yes.
Yes, sir. In the beginning, when you talked about complexation of metals with arene complexes, like both electron withdrawing and electron donating seems like they are not suitable. So only alkyl alkyl benzenes or things like that are possible.
No, I probably did not choose enough examples. It's possible to have, if you do co-condensation method, it's possible to make it with a wide variety of substituents. Okay. Even chlorine, for example, chlorine, I said that if you have a halogen, it is capable of interacting with AlCl3, and so you can't use the Fischer-Hafner method of synthesizing aromatic metal complexes, benzene, arene ring complexes, ring systems. But if I have the co-condensation method, I can use any other method, any other substituent, chlorine, cyano, etc.
But the electron donating groups are difficult, and from the metal carbonyl complexes, they are not accessible.
Sorry,
Metal carbonyl.
metal half sandwich complexes.
Half sandwich or sandwich complexes. Sandwiches are not coming from
Wait,
metal
wait, wait,
carbonyl. Yeah.
wait. Sandwich complexes are unique as far as aromatic ring systems like C6H6 go. And the reason is you can't convert, you can't make that easily unless you generate the metal atom and prevent it from uh, interacting with any other ligand. Okay, the moment you give it a chance, it will go to a half sandwich complex or something else, right? Uh, that is why you need the co-condensation technique when you have a chloro substituent, etc. That limitation is not there when you are trying to make a half sandwich complex. Half sandwich complexes are easier to access and you can make them directly from metal carbonyls and the ring system directly. That's what I illustrated in the latter half. And
Yes.
they are more rugged.
Now it's clear. Thank you.
Yeah. And they're more rugged. Yeah, Arco.
Sir, can you explain again why the gap between the sigma and pi orbitals is higher in comparison to metallocene?
Okay, I just read it this morning in Elschenbroich's book. I have not checked this out computationally, nor have I read it elsewhere. But I mentioned it because in his figure, the figure that he draws, this is mentioned in the book. This is the figure that he gives. And he says that this gap is higher. Okay. This gap is higher. And this gap is also higher, larger.
Okay.
Okay. So this is directly from his book. I said this, and the reason why he said this is because the EPR spectra of ferrocene is a bit confusing. If you draw a simple molecular orbital picture, you get dz squared as a highest occupied molecular orbital. But when you oxidize it and form the radical cation, it is in a degenerate set of orbitals, which suggests that this group of orbitals are in fact lying above the dz squared. Okay. So this is a complication in metallocene. It's like ferrocene. Whereas when it comes to bis-benzene chromium, he says that the gap must be larger because the oxidized species is clearly lying in a dz squared orbital. So that is the reason why he feels that this gap is larger. We can quickly take a look at the calculation that I have done, which I just showed you. Someone's phone is echoing. It's it's not mine for sure. Okay, so here is the bis-benzene chromium, and if I look at the let's see this. Um, okay, this is bis-benzene chromium. No, sorry, this is not bis-benzene chromium. This is yeah, this is bis-benzene chromium. Okay, so here you go. This is the dz squared orbital, and if you look at the this is the highest occupied molecular orbital, 2 electrons. This is the next lower one, and that is d x squared minus y squared, etc. So in order to do this, in order to visualize this well, you need to change this, which I have not told you all before. So here you go. This is the next lower homo minus, what is called homo. This is homo, and this is homo minus 1. And homo minus 2 is just the degenerate set of orbitals. Okay, dx squared minus y squared and dxy. So those two orbitals. it's 1.63 and 0.163 and 0.147. When it comes to ferrocene, we'll take the D5H to D5H. This is again the eclipsed form of ferrocene, which I have generated. Then you find the, let's see where we are. Here is the highest occupied molecular orbital. This is a DFT calculation, and it actually puts the dx squared minus y squared and dxy above the dz squared. Okay. So here, of course, the gap is, we can check the gap. The gap is 0.04, 0.03, 0.03. I don't remember now. I think that was 0.04 in the other case. So the gap is higher, even in a DFT calculation, the gap is higher. And that can only be explained as better interaction with the system that I told you. It seems to be a better donor or better acceptor, whichever way you, both orbitals are higher and lower. But bond energy is less. That's the difficulty that I had in understanding this, because bond energy should also be higher for bis benzene chromium. That's not the case. That's why I said that it's the electrostatic effect in CP2Fe that is making it more stable. Okay, I think we have overstepped the time. Is there any other question, pressing question? Otherwise, we will stop here. Okay, we'll meet only on Monday next, because I will not be taking class on 25th. It's a holiday, so we'll meet on Monday. And is there, I will send a questionnaire. I want to have probably one discussion class, because we do not get time for discussing some other points that I want to discuss. So every time we are running out of time. So, okay, so we'll meet on Monday. You can all leave.
So do you have any exams?
Yeah, 30th we said, no?
30th, yeah.
Yeah, 30th is Wednesday. We will have an exam, in-class exam.